Hello and welcome to episode 2. In episode 2, we are starting to look at the point groups that are depicted by the equilateral triangle. So we're going to start at the highest point group symmetries and then work our way down. So here is one of the models. So we see an equilateral triangle, and for our equilateral triangle we see the point P. So that is the point of the point group that will not move during the symmetry operations. So this is the bottom piece of our pattern, so it's shaped like a triangle. So to demonstrate the point group symmetries, let us take one of our pre-constructed triangles, and we see this particular triangle has the same substitution at each vertex. So we see 3 greens. So a molecule in real life that would exhibit this type of molecular geometry would be boron trifluoride, very, very important Lewis acid catalyst in organic chemistry, and a trigonal planar compound. So we're going to investigate the symmetries of that type of molecule. So one of the most important symmetry operations that we are concerned with is the C3 operation. So we'll see, and to build a C3, we notice that we have our central point here. So we can make a small point with our push pin, and then we can make another push pin right there, P, and we will combine both pieces of our model. So see if we can do this and point directly through the same holes. There we go. So now we have both. And we can push our pin into a eraser. It's a nice safe way to do it. So now we notice that if we line up substituents, what I really want to do is, instead of using this background, I want to use this one. So essentially have 2 identical equilateral triangles, and they're substituted exactly the same way. Then we can line these 2 up. And push the spin right. Now the advantage of doing this way is that we can see that if we take our upper triangle and rotate it by 1/3 of a turn, by 120 degrees, or 2/3 pi, that it lines up exactly the same way as before. And we notice that if we look behind each green, there's another green. So we see that if we turn it by 1/3 of a turn, it looks exactly the same as it did before. So let's try it, but this time we're going to turn clockwise. So let's turn clockwise by 1/3 of a turn. And we notice that if we turn clockwise 1/3 of a turn, that the green atoms line up again. So if we were to turn it by 1/3, either clockwise or counterclockwise, we won't notice any difference. Come upon it this way, we won't notice that it had ever been turned. So we say that this 1/3 of a turn we call a C3 operation. By convention in mathematics, we consider the angles to go counterclockwise. So a C3 operation is a 1/3 turn counterclockwise. Now we also notice that if you turn it clockwise by 1/3 of a turn, it also looks the same as it did before. So this particular symmetry operation also has to belong to this particular molecule. So by convention we call that C3 to the -1. So that is in the opposite direction. We give it the exponent of -1. So C3 and C3 -1 are both symmetry operations of the group. And we also notice if we make 2 1/3 turns, so there's one 1/3 turn, and now a second 1/3 turn, that again, the green atoms all line up, so we can see that C3 squared is also a symmetry operation of the group. So C3 followed by C3 we can write as a multiplication, and we can call it C3 squared. So we see that in this particular point group, now this is the point group which we call D3H, and this C3 operation is the highest C rotation that is found on the molecule. And we'll see what the other rotations are in a minute. But one of the first things we want to do whenever we are investigating a new molecule in group theory is to find the high order rotation axis. So for example, a C3 trumps a C2 because 3 is bigger than 2. So if you have both a C3 and a C2 rotational axis on our molecule, the C3 is the one that we're interested in. If we have C4, C4 would trump C3. The important thing is that if we have a high order rotation axis that is 3 or more, that leads to very special consequences for the molecule, particularly a phenomenon which we call degeneracy. And when we talk about degeneracy, we're not talking about smoking cigarettes and shooting pool in River City. That's not the type of degeneracy we're talking about. In degeneracy in chemistry and physics means that we have 2 or more states that have exactly the same energy. They're not close to the same. They're not the same within experimental error. They are exactly the same, and they are exactly the same by geometry. So that is a very, very important consequence. So a molecule such as boron trifluoride, because it has this C3 axis, and C3 is more than 2, it has this phenomenon called degeneracy. Now this particular molecule belongs to a point group which we call D3H. And we'll get to why the D and why the H, but at least as far as the 3 goes, when we name groups, we often include the highest order rotation axis in the naming of the point group. So in this particular point group, we call it D3H because it has a C3 rotational axis. The C means that it's a so-called proper rotation. Later on we'll learn about improper rotations. So for the time being, this is our example of a C3 operation. Going in this direction is a C3 to the minus 1. Now one of the things that we can do as far as rotational axes is to examine what happens to our molecule if we start to substitute. So for example, let's substitute one of the greens. Actually, substitute 2 oranges. So now we have a slightly different shape. So now maybe we have 1 fluorine but 2 chlorines. And let's see what happens as far as the high order rotation axis when we do this substitution for our triangle. So this might be BFCl2, for example. Push a bit in there. So now we want to see if it has a C3 operation. So let's rotate by a third. So now we rotate by a third. Something different happens. Now we have an orange where a green should be. We have a green where an orange should be. An orange is the same. But if any of the atoms change when we do the operation, if any of them changes at all, that means this particular operation is not an operation of the molecule. So the molecule does not have C3, because if we rotate by a third of a turn, all the atoms don't go to equivalent spaces anymore. In other words, if we turn it by a third, it doesn't look the same. We can tell it looks different. So it does not have C3 anymore. It does not have C3 minus 1 either. So let's try going in this direction. Now some of the atoms will line up, but for it to be a symmetry operation of the group, we have to have all the atoms line up. So we see that we no longer have C3. Now because this does not have a C3 operation, we no longer have degeneracy. So this particular group is a group called C2V. And to see where the C2 operation is, we have to disassemble the molecules temporarily. And we would see that the axis is along this line here. So we take this line and rotate the whole molecule by 180 degrees, which we call a C2 operation. It looks the same. We have oranges up here and green back here. So we again rotate by 180 degrees, a C2 operation. We see that this molecule does have C2. So C2 is the highest order rotational axis. Now that leads to the naming of this particular point group called C2V. So that is the C2 goes along here. Now as far as the V goes, we can exhibit that particular symmetry operation along this line. If we take the molecule and we fold it along this line. This is where the mirror plane would be, the plane that cuts it perpendicular to the plane of the molecule. We fold it over, and we see that when we fold it over, orange goes with orange, green goes on itself. So if we fold it over, it looks exactly the same. Now we can also demonstrate this, that we'll try to do, with a mirror. And if we do it with a real mirror, you can actually see the meaning of mirror plane. So let's see if we can get this to work here. Maybe a little tricky getting the angle for the camera, but this is the idea. So we can see that it really does look like the mirror reflection of what's behind if we move the mirror out of the way. So this is a molecule point group which we call C2V. So we've gone from D3H down to C2V by substituting. So having 2 of one and 1 of another is different than having 3 of the identical substituents. Now the last group, we shall see, and we should have some more here. Here we go. There. Okay, let me go get there should be a CS one.